It's wonderful to be here. Let me just turn this around. So I want to tell you a little bit about some of the recent work that has been going on in my group with colleagues. And this is mostly centered around sort of understanding and demystifying what is known as acceleration phenomena in first-order optimization algorithms. And as you all know, first-order optimization is sort of, even though it's a very old topic, it's the flavor of the day because in large-scale machine learning applications, we can't afford to store and process higher-order curvature information. And so we want to speed things up. As you'll see, the standard first-order methods are gradient descent and its variance. They're sort of slow, and there are ways of speeding it up. And this talk is basically two little vignettes, two small results about attempting to sort of understand where this acceleration phenomena is coming from. This is mostly the work of my PhD student, Jingjiao Zhang, with input from my postdoc, Aryan Mokhtari, and together with my colleague, Subrit Straw, who's faculty at MIT. Okay. So, and this is, at least the first part, is based on a paper that is available on arXiv and also on, that I presented a few weeks ago at this NeurIPS meeting. So, I mean, all audience here is sort of familiar with sort of basics of continuous optimization. You're trying to minimize a function, and you have access to the function value and its gradient. And we all know, you know, convexity is a wonderful thing. Basically, one way to interpret it is that a linear approximation of a function is a global under-approximator. So you, based on local information, you learn something globally about the function. So the first part of the talk is going to be about optimizing functions that are convex, and I'm going to comment on non-convex a little bit as well, and also have this property where the gradient is Lipschitz smooth. So, so this is sort of the standard setting that has been, you know, studied for years and years. In some ways, in optimization, we've had a regression. We've regressed to the more basic things. When I was an undergraduate and then a graduate student in 90s, all the rage was about interior point methods and semi-definite programming and all of that. And sort of we regress now to sort of more basic things because this is supposedly the age of big data. So, of course, what people do is, you know, generally some variant of gradient descent. Of course, a lot of it is stochastic variance, but that's sort of immaterial for the core, the gist of the discussion. And turns out that because of the reasons I mentioned, using second-order information, if you're trying to do, say, empirical risk minimization for in machine learning, for supervised learning, you have a deep neural network model, you're trying parameters, don't worry about the non-convexity. That doesn't quite matter for the parts that I'm going to talk about here. But the issue is you can't store really in this high-dimensional space high-order information. So you want things to be simple. So you use the function value. Your oracle basically can give you access to function and its gradient or stochastic gradient. But of course, we know gradient descent is slow. And it turns out, and we've also known this for some time, that acceleration can help. But exactly how and why it's helping, and how can we sort of tweak it to get a family of algorithms, that's sort of more mysterious. So the phenomenon of acceleration essentially, as well, we'll see throughout the talk, essentially boils down to using, sort of going back to the work of Polyak in 60s, the so-called heavy ball method. And so the idea is that if you think about gradient descent as just following the gradient of a vector field, or having some kinematic model where you follow a differential equation x dot equal to negative gradient of v, the accelerated methods typically try to simulate a second-order dynamic. So it's a heavy ball that is moving with some friction. That's sort of the key idea. And if you look at most methods for whether you use some variant of SGD, they always have this extra acceleration term there to speed things up. And they can sort of help improve the iteration complexity or number of iterations by several orders of magnitude. And the two quintessential acceleration methods that are very related, and the differences between them are somewhat mysterious, are one is the sort of the classical Polyak method, which I'll describe, and then so the slightly more recent but still old news Nesterov's accelerated gradient. So I'm going to describe both, and I'll tell you what the mysteries are in here. So this is, I like this picture. This is in a tweet. So it's like a paper by tweeting, a picture that Sepp Bubek sent on Twitter a while ago. This is very, because by choice of notation, you can sort of catalog all these methods into one simple picture. So basically, all we do is we define the x plus, which is the next iteration. Think of this as an operation where you take x and you subtract some fraction of the gradient. So call this the gradient step. And then call something we call dt. And this is sort of the momentum step that is the difference between xt and xt minus 1. We call this the momentum term. So if you say xt, if you write the dynamics xt plus 1 as xt plus, that's gradient descent that goes all the way back to Cauchy. If you do xt plus 1 is xt superscript plus this momentum term, right? I.e. the gradient is evaluated at x, then this is the Polyak's heavy ball method with an appropriate choice of the step sizes here, eta and gamma, the two parameters that you have to tweak. But then something interesting happens. If you do the plus of xt plus dt, right, not xt plus dt, so yeah, so x plus is this operation of x minus something times the gradient of f, like some step size minus the gradient. So the difference between the two really is where you evaluate the gradient, essentially. Okay. So, so people have observed that this actually speeds things up. It turns out that in early 80s, this was studied by Nesterov and Nemirovsky in terms of, okay, what is the oracle complexity of first order, optimization algorithm? So if among all algorithms that have access to the function value and its gradient, what's the optimal one? Turns out gradient descent is not optimal, but these accelerated methods could be with the right choice of parameters. And that's why people are interested in it. Okay, so there's a nice whole story about how you should tweak things. And in fact, one of the challenges that the acceleration presents is that this extra term, as for control theorists in the audience, if you sort of, as we will see, if you think of the continuous limit of this, this is like adding an integrator to your gradient dynamics. okay? And this could have a destabilizing effect. And so it's important that these parameters be chosen very carefully. Otherwise, they will be destabilizing. Even when they're stable, it turns out there are other issues with this, that they can essentially amplify noise. So the parameters have to be chosen judiciously. But the point is there's a cookbook way of doing this so that things get sped up, basically. And so, but we want to understand how and why this works. So what do we know so far? First of all, the two algorithms look essentially the same. You know, the only difference being that in one case, you evaluate the gradient at step xt, that's the Polyak method, plus the momentum term. In the Nesterov method, you evaluate the gradient somewhere between xt and the next one. So you do xt plus gamma times the difference between xt and xt minus. So where the gradient is evaluated actually matters. Okay, turns out that, you know, Polyak proved in his mid-60s paper that by finding the appropriate step size, you can provably get acceleration for convex quadratics, right? So for convex and strongly convex quadratics, there's a formula for choosing the step size so that you get the optimal, the best possible rate that you could get. It turns out for, as we will see in a little bit later, but let me just say it, for convex functions that have Lipschitz gradients, and they're not necessarily strongly convex, the optimal rate is 1 over t squared, where t is the number of iterations. And if it's strongly convex, meaning that the Hessian is lower and upper bounded by basically positive multiples of identity, then in that case, the optimal rate is square root of condition number. And you see why gradient descent is not optimal, because gradient descent gives you a rate that is the condition number itself, not the square root. Okay? If anything is, this is very informal, so if anything is unclear, please do. If you don't understand any of the terms that I use, please let me know. And the proof techniques for this, you know, is very standard. You know, you open up any of the many books of our colleague Dimitri, you'll see, you know, it's basically 2-3 lines of inequalities to prove where this dependence on convergence rate, this condition number actually comes. Okay, so the interesting thing is this, the Polyak method, which was evaluating the gradient at x and then adding the momentum term. For quadratics, it gives you the optimal rate. So you would think if I have a strongly convex function that is not a quadratic, because it's upper and lower bounded by quadratics, then it should also give you acceleration for those as well. It turns out that's not true. So unfortunately, Polyak's method doesn't quite work for general convex functions. And in fact, the rate could be, if you choose the step size wrong, it could either result in oscillation, so you could introduce limit cycles, or you could get rates that are worse than the rate that the gradient is. Now there comes Nesterov's fix to this. But the way that Nesterov proves it is kind of mysterious, and it seems like a one-time trick that works for the particularities of that problem. And it doesn't give you insights, by his own saying, to generalize, to understand where this is coming from. So people, suddenly this has become a hot thing in this community in machine learning that is focused on optimization. So there's so to try to understand where is this acceleration is coming from, what's the differences between Polyak versus Nesterov, and you know, every month there's like 5 papers on this on arXiv. So there's Sepp Bubek and co-authors had this nice paper that he described on his blog. By the way, I recommend his blogs. You know, he's very clear and nice tutorial value and a lot of things. He tried to provide some geometric insight, but again, it was like starting from the Nesterov proof and then mapping it out to something else, as opposed to trying to come up with an independent insight from it. Then there was this interesting paper by Laurent Lessart and Ben Recht and Andy Packard from a few years ago, which sort of explained this phenomena here that I mentioned, that why, that the fact that Polyak's method works for quadratic functions, but somehow it doesn't work for strongly convex functions that are upper and lower bounded by quadratic. But it turns out what they observed here, as I told Ben, when he talked to me about this in 2014, this is, anyone who's taken a course in absolute stability and in nonlinear control recognizes this. What they proved essentially is fallacy of something called the Eiserman conjecture in nonlinear control. So in 1940s and 50s, there was a group of Russian control theorists and mathematicians that were obsessed with this problem of stability of a relay system, where you have linear dynamics connected to a nonlinear uncertainty block that could be a saturation block, it could be a relay, it could be something that is represented by a sector-bounded nonlinearity. This is called the Luray problem. So there was this conjecture in 48 that if a feedback system is stable for any sector-bounded nonlinearity that is linear, i.e. for any linear foliation of this sector, then it has to be stable for any increasing nonlinearity that falls within that sector. It kind of sounds like it should be true, but it's not. And turns out that this observation that made a lot of sort of news here, that Polyak's method works for quadratics, but it could be destabilizing for strongly convex functions that are bounded by quadratics, is just an example for that untrue conjecture. So, okay, so we know that, and the machinery that people in robust control have developed for sort of generalizing these absolute stability conditions can actually come up with computational ways of choosing the momentum term and the step size to give you the best convergence rate. But unfortunately, these are based on semi-definite programming problems. It's not symbolic. So if you give me the function, I could plug it in, and so I can't give a theoretical insight from, or I could, like, if you give me a family of problems, I could sort of grid the hell out of it and tell you by simulation what the rate is, but not. But if I wanted simulation, well, I could simulate the actual trajectory, right? So, okay. So the question is, what can we say about this? Recently, there's been a lot of focus on sort of understanding the ODE representation of it. So let's see where the difficulty comes from. So this is the gradient descent. We said, you take the function, some step times the gradient. If you, of course, it's not a surprise, if you set the step size to 0, then you get this gradient dynamics. Okay? And, it's easy for anyone who's had a basic course in dynamical systems to construct, let's say, the function value, if the function is convex, could be basically a Lyapunov function, and you can sort of prove stability of this algorithm, or this the equilibrium of this differential equation, and you get you improve a rate of sort of 1 over t. And that's why we said it's not optimal, because the rate for a convex function that is not strongly convex, the optimal rate is 1 over t squared. So if I'm here, then I can do Euler discretization and get this back. So let's see if we can do the same thing for Nesterov's problem too. This was sort of the mysterious dynamics that gives you acceleration. So let's see. It's basically the same thing that I told you. It's just written in terms of 2 variables. So this one, xk plus 1, is yk. minus eta times gradient of f evaluated at y, right? But what is y? Y is x plus beta times xk minus 1, right? That's the moment. And you have to choose these eta and beta parameters. So there was this paper by Sue, Boyd, and Candace in 2014 and 15, which basically said that if you take if you let the step size of the Nesterov's accelerated gradient scheme go to 0 for when the function is strongly convex, then you get this heavy ball ODE, same as the ODE that Polyak started with, but with a time-varying friction term. Okay, and there you can, for this, you can get this optimal rate of 1 over t squared. The problem is that you can set the step size go to 0, and you get this, but there are many algorithms that can converge to this ODE. That doesn't mean that there is a discretization that can go from this ODE and give you Nesterov's algorithm or something that achieves that rate. Okay? Okay, so, yes. Yes, so what I said is if you let the step size go to 0, then you get this ODE. But you can't construct the algorithm from a discretization of this ODE. Exactly. Different discretization schemes lead to different algorithms, and it's not clear which one of them give you acceleration, right? And as you will see, getting so by acceleration, I mean this rate of 1 over t squared because gradient descent is 1 over t. Yes. So think of it as numerical integration. So I have to somehow, I have this differential equation. I want to plug it into a computer. Like the standard thing I could do is replace x dot with xk minus 1. That's backwards Euler. I could do forward Euler. That's like a first order integration scheme. As you will see, I can have higher order integration schemes. Yes. So what we're saying is that this heavy ball ODE is the continuous limit of the Nesterov algorithm. But because we can't go back, because I don't have a discretization scheme that achieves Nesterov or anything like that, I don't have an algorithm that gives me acceleration. This is some algorithm, but we don't know where is it coming from. I want an algorithm that gives me 1 over t squared. Well, so when the step size goes to 0, yeah, so I'm skipping some detail here. Yes, which is this paper. Yes, it's this paper. But the 0th order bit of it is that as you set the step size, you make it smaller and smaller and smaller so that the derivative is better and better and better approximated by xk plus 1 minus xk, right, over some epsilon. Yes. So that's basically, think of it this way, that, I take xk plus 1 minus xk over eta, and I approximate that as x dot, and now I want eta to go to 0. That's roughly. Yes, so up to here, the function is, well, it has Lipschitz gradients. Yeah, the gradient is Lipschitz. Yes. Exactly. And Nesterov has a proof that this gives you 1 over t squared. But the proof is very convoluted and doesn't tell you, doesn't provide a link between this continuous intuition. Yes, absolutely, absolutely. That's exactly the point. Yes. Any other questions? Okay, so it's not surprising, and anybody who's worked with any dynamics would see this, that if I just take this ODE for which I can prove a rate, and I do an Euler discretization, if I'm not careful with things, then it could be unstable. And so here's where you're stuck between a rock and a hard place. Because when you want to discretize this ODE, you want somehow to inherit the Liopunov function that proves stability of the equilibrium of the continuous one, right? But if you make the step size too small so that this is a faithful approximation, then you lose the acceleration. Then your estimate of the rate for the algorithm would be even worse than gradient descent. No, it's more, you'll see it. It's more complicated than that. So this paper is a very nice paper by Andre Wibisono, who was actually a student of Michael Jordan and Pulling's postdoc, and Ashia Wilson, called A Variational Perspective on